Picture this, okay? It is July 10th, 2026. You are out floating on a boat in the South China Sea, and you look up.
Just minding your own business.
Right, minding your own business, and you see this 63-meter-tall skyscraper, basically a 20-story building just plummeting out of the sky.
Oh, and it's falling at terminal velocity, engines just absolutely screaming as it tries to brake.
Exactly, but instead of aiming for a solid concrete landing pad like we're all used to, it's dropping directly toward a giant high-strength net.
Strung across this massive ship in the middle of the ocean.
Yeah, the rocket hits the net, the cables just scream under the tension, and then it just stops. It is suspended there midair, swaying gently above the waves.
I mean, seeing the footage of that capture, it felt like watching a glitch in physics. We're so used to seeing rockets land on solid ground, resting on their own legs, that watching one get swallowed by a floating spiderweb genuinely scrambles the brain a little bit.
It really does. So today, we are doing a deep dive into this. We're tearing into the technical blueprints, the SpaceX engineering reports, and even some real-time observer data from the maiden flight of China's Long March 10B.
We really want to figure out exactly how they pulled off this sci-fi capture.
Right, because if this were just an engineering stunt, it wouldn't really matter.
Yeah.
But this net catch system, it's actually the linchpin for two massive global shifts.
Oh, absolutely. The deployment of mega-satellite internet constellations and the rapidly accelerating race to put crews on the moon before 2030.
Yeah, big stakes. So to really grasp the magnitude of what the Long March 10B achieved, we sort of have to look at the ceiling of current aerospace engineering, right?
Yeah, for sure. Because for over a decade, SpaceX's Falcon 9 has been the absolute gold standard for reusable rocketry.
Right.
And their method involves the booster coming down and at the final second, deploying 4 large hydraulic landing legs to touch down vertically on a drone ship or a land pad.
We've all seen those videos.
Yeah.
I mean, it never gets old.
Never.
But reading through these CASA-C reports, they point out a fundamental flaw, or, well, maybe not a flaw, but a hard physical limitation in that method.
Yeah, because the Falcon 9 carries its own landing gear.
Right. And in aerospace engineering, that is known as the dry mass penalty.
Exactly. Every single ounce of those hydraulic landing legs, the heavy-duty actuators that deploy them, the reinforced structural mounting points.
The buffer mechanism.
Yeah, all of it. All that dead weight has to be carried from the exact moment of liftoff.
Even though the rocket only needs those legs for, like, the final 5 seconds of a mission.
It's wild when you put it like that.
It's like, okay, imagine trying to summit Mount Everest, but you insist on carrying a heavy, king-size mattress strapped to your back the entire way up.
Just a massive mattress.
Right, and you're doing this just so you have something soft to land on when you jump off a tiny 10-foot ledge at the very end of your descent.
That's actually a great analogy. Sure, it protects you from the fall, but that mattress took up, what, 30% of your backpack space?
Exactly. Space that could have been used for extra oxygen or food or, in a rocket's case, more satellites.
And the rocket equation is incredibly unforgiving. Every kilogram of unnecessary dry mass you carry requires exponentially more fuel to lift it off the pad.
Which means less payload.
Right, which reduces your payload capacity. The sturdier you build those landing legs to survive a hard touchdown, well, the less cargo you can actually deliver to orbit.
So the paradigm shift with the Long March 10B is that they looked at the mattress problem and decided, you know what, let's just leave the mattress on the ground.
Or, well, on the ocean in this case.
Right. They totally outsourced the landing gear.
Completely. By eliminating the heavy hydraulic legs, the Long March 10B only has to carry 4 lightweight arresting hooks built into its aft section.
Wow.
Yeah, so all the heavy lifting of the recovery, the shock absorption, the stabilization, the physical infrastructure, all of that is shifted off the rocket and onto the recovery vessel.
And that vessel is not some, repurposed barge. It is a purpose-built ship called the Pilot, or Linghangza.
Delivered in November 2025, if I recall.
Yeah, and this thing is a Leviathan. I mean, it measures 144 meters long by 50 meters wide.
Oh, wow.
It has a full load displacement of 25,000 tons.
Yeah.
Just sitting out there in the ocean, waiting to catch a falling skyscraper.
Which, by the way, requires an orchestration of logistics that borders on the impossible. The timeline of this flight profile is where the engineering gets just incredibly dense.
So let's actually track that descent. The Long March 10B launches from the commercial spaceport in Hainan.
Right.
The stages separate in the upper atmosphere. The upper stage continues on to deliver the payload. But the first stage, this 5-meter diameter booster, powered by liquid oxygen and kerosene, begins this extreme 6-minute return journey.
Just 6 minutes to bleed off thousands of kilometers an hour of velocity,
Yeah.
to navigate through the atmosphere and somehow thread the needle into a net 430 kilometers downrange in the South China Sea.
It's terrifying. And as it falls, we actually found this incredible detail from some spaceflight forum observers who were tracking the descent.
Oh, I loved this part.
Right. People watching from the coastline suddenly saw this thick, terrifying black smoke billowing out from near the top of the booster.
And the immediate reaction online was just total panic. People naturally assumed that the core structure was failing or an engine had ruptured.
But the reality of atmospheric reentry is just incredibly violent.
Yeah, that black smoke was actually a feature, not a bug.
Wait, really?
Yeah, it was the composite materials of the inner stage, so the section that connects the first and second stages. It was basically ablating and burning away due to the extreme friction and heat of punching back through the thick lower atmosphere.
So it's supposed to do that.
Exactly. The core systems, the pressurized tanks, the engines, they were holding perfectly stable inside that fiery envelope.
That is so intense. And as it comes through the atmosphere, it obviously has to steer.
Yeah.
The reports mention it adjusts its attitude using grid fins.
Right, the grid fins.
But I've always wondered, how does a falling metal cylinder actually change direction in midair?
Well, if you look closely at the footage of these returning boosters, you'll see these flat, waffle iron-shaped structures fold out near the top.
Okay.
Those are the grid fins. As the rocket falls at supersonic speeds, the air rushes through the little square holes in the grid.
Oh.
So by tilting those fins even slightly, they create immense aerodynamic drag and lift on one side of the rocket. It basically allows the flight computer to steer the falling booster, much like a skydiver using their arms and legs to glide to a specific drop zone.
That makes a lot of sense. So it glides toward the pilot ship, it reignites its engines for a powered braking burn, and it hovers over the net.
Right, the critical moment.
And this is honestly where I struggled with the physics of the Sakasa Sea design. A ship pitching and rolling in the ocean waves seems like the absolute worst possible place to try and thread a falling rocket.
It sounds like a terrible idea at first.
Right, because with rigid landing legs on a flat deck, if the ship rocks a bit, the legs can at least distribute the weight and lower the center of gravity. But aiming for a net while the deck is swaying, that just sounds like a recipe for the rocket slicing through the cables or tipping over and exploding.
Yeah, and that intuition makes perfect sense if you're imagining a static, rigid net. But the engineers at CSC, they actually used the dynamic nature of the sea to their advantage.
Oh, so.
Well, a rigid flat pad requires the rocket to match the exact angle of the deck at the exact moment of touchdown.
Right, otherwise it tips.
Exactly. If the ship pitches 5 degrees, the rocket hits at an angle and risks falling over. But the cross-shaped, high-strength buffered net on the pilot is designed to accommodate that movement.
Kind of like a giant trampoline.
Well, actually, a trampoline is the opposite of what you want here.
Oh, really?
Yeah, because a trampoline stores kinetic energy and throws it right back at you.
Oh, true. It would bounce the rocket back up.
Exactly. This net is an energy sink. It's designed to swallow the momentum completely. So the flexibility of the net effectively enlarges the capture window. It gives the rocket a larger margin for landing deviations than a rigid flat pad ever could.
Because the net can mold to the angle of the rocket, rather than forcing the rocket to mold to the angle of the deck.
Precisely. But, the capture is still incredibly active. The pilot uses a dynamic positioning system, firing multiple thrusters continuously to hold its exact GPS coordinate against the ocean currents.
Wow.
And at the 4 corners of this massive platform are high-power LiDAR units.
LiDAR, so using pulsing lasers to map out the physical space in 3D.
Yeah, but these aren't just measuring distance. These LiDAR units are continuously mapping a dynamic, pitching environment through ocean spray and rocket exhaust.
That's a lot of interference to cut through.
It is, and they autonomously track the rocket's exact position, its horizontal velocity, and its attitude, so its tilt in real time.
So the ship and the rocket are just constantly communicating, adjusting to each other.
Exactly. As the rocket hovers just above the net, it brings its horizontal velocity to absolute zero. It aligns itself perfectly vertical, and then it just cuts the engines and drops.
And those 4 lightweight arresting hooks on the side of the rocket engage the grid of the net.
Yep.
But, a 63-meter skyscraper falling even a few feet has a massive amount of kinetic energy. How does it not just tear the net off the towers?
And that brings us to the energy dissipation mechanism. Because the net isn't just statically tied to the metal posts.
Okay, so what is it tied to?
The specialized cables making up the net are actually connected to massive hydraulic dampeners built into the deck of the pilot.
Oh, wow.
Yeah, so as the rocket's hooks grab the net and pull downward, that immense kinetic energy pulls on the cables.
On the cables pull on pistons.
Right, the cables pull on hydraulic pistons, which then force hydraulic fluid through tiny, highly calibrated valves.
So it literally turns the kinetic energy of the falling rocket into heat inside those hydraulic valves.
Exactly. It bleeds the energy away smoothly. It stretches and gives, layering the resistance so the downward momentum is eliminated gradually.
That's brilliant.
It brings the rocket to a complete halt, suspended motionless in the center of the net, without buckling the rocket's incredibly thin metal skin.
It's like the engineering equivalent of catching a raw egg thrown at full speed without breaking the shell.
Exactly that.
Or structurally, I guess it sounds a lot like a fighter jet landing on an aircraft carrier.
The physics are nearly identical, honestly. A fighter jet uses a tail hook to catch an arresting cable, and the hydraulic engines below the flight deck resist that pull, bringing a jet traveling 250 kilometers an hour to a stop in seconds.
Wow.
The Long March 10B is executing that exact same energy transfer, just, vertically.
That's wild. And by doing all of this, by shifting the hydraulic dampeners from the rocket to the ship, they rewrite that dry mass equation we talked about.
Right, leaving the mattress behind.
Exactly. The rocket is significantly lighter, which means it can pack in a lot more fuel or, more importantly, carry way more payload to space.
Which pivots us from the engineering to the economics.
Because building a 25,000-ton automated catcher ship with LiDAR and hydraulic dampening nets, that is a multi-billion-dollar endeavor.
Oh, yeah. You don't build infrastructure like that just for a science experiment.
Right, so what's the driver here?
The driver behind this colossal investment is severe, immediate market pressure, specifically the race to dominate low Earth orbit.
Ah, okay, we're talking about the Thousand Sails and Guang satellite internet constellations.
Exactly. China is actively working to deploy tens of thousands of satellites to rival systems like SpaceX's Starlink.
And deploying a constellation of that scale requires absolute brute force launch cadence.
You need two things above all else: an incredibly high flight frequency and a drastically lowered cost per kilogram to orbit.
Because building a brand new rocket for every single launch of a 15,000 satellite constellation would bankrupt any space agency on Earth.
Instantly. The math for the Long March 10B is built entirely around that specific problem.
So in its reusable configuration, meaning it saves enough kerosene and liquid oxygen to perform that extreme 6-minute return flight and get caught in the net, this booster can still lift 16 metric tons to low Earth orbit.
Which is huge. 16 metric tons is a massive payload capability for a fully reusable first stage.
Right.
It allows KSC to perform clustered satellite deployments, stacking dozens of constellation satellites into the fairing and dropping them into orbit on a single flight.
I keep looking at the maintenance side of this equation, though. Like, we talked about shedding the rocket's dry mass to save money on the launch.
Yeah.
But salt water is the absolute worst enemy of aerospace hardware.
Oh, it's terrible.
Right. So does the massive operational cost of maintaining the pilot, the dynamic positioning fuel, the port fees, the crew, constantly fighting saltwater corrosion on those highly sensitive hydraulic nets and LiDAR units, do all of those terrestrial costs eat into the savings you get from making the rocket lighter?
Well, that is the debate currently raging in the aerospace industry. The economic validation of a sea capture system doesn't come from a single successful catch on July 10th.
Okay, where does it come from?
It comes entirely from the fleet turnaround time.
So how fast they can hose it off and fly it again?
Exactly. CAS-C has publicly stated their goal is to refly this exact recovered booster before the end of 2026.
Wow, that's fast.
Yeah. If they can bring the pilot back to port, crane the rocket onto land, inspect the engines, clean the sea salt out of the valves, and put it back on the launch pad in a matter of weeks, then the economics completely flip.
Because the volume makes up for the fixed costs.
Right. If that 25,000-ton ship can catch 50 rockets a year, the fixed costs of the ship evaporate across the volume of launches.
But if it takes months?
Conversely, if it takes 6 months to refurbish the rocket because the ocean environment corroded the turbopumps, the net catch system fails as an economic model.
So the reflight is the real crucible here. A single recovery proves the physical capability under one specific set of weather conditions. But the reflight proves whether this can actually function as a commercial airline model for space.
which is vital not just for internet satellites, but for the ultimate goal of the Long March 10 architecture. Because this rocket family is not designed solely for commercial cargo.
Right. The sources actually tie this directly to humanity's biggest upcoming milestone. The Long March 10 family is specifically tasked with sending Chinese astronauts to the lunar surface before 2030.
Yes, the rocket we are analyzing, the Long March 10B, is really the cargo-optimized vanguard of a modular family.
Okay, so how does it fit into the moon missions?
Well, when you plan a crewed lunar landing, the mission architecture requires multiple heavy-lift launches. You need one massive rocket to launch the crew capsule, and you need another to launch the lunar lander into orbit so they can dock.
And if you're throwing away massive multi-million-dollar boosters for every single lunar mission, sustaining a presence on the moon becomes financially impossible.
Exactly. So by testing the Long March 10B with this net capture system right now, they're conducting live validation of the flight hardware that will eventually power those moon missions.
So it's double duty.
They're validating the reliability of the engines to reignite in high-stress environments. They're proving that the composite materials can handle the thermal load of reentry without degrading the core structure.
Right.
And they're testing the precision navigation software required to safely transport human beings. Every catch they make at sea builds the flight-proven heritage of the lunar program.
And what's crazy is they didn't just wing this on July 10th. The foundation for this catch was actually laid months earlier in a critical precursor test back in February 2026.
Oh yeah, the February test was a brilliant piece of dual-purpose engineering. They launched a prototype of the Long March 10 first stage from Wenching to an altitude of about 105 kilometers.
So just past the edge of space.
Right, and during that flight, they tested the launch escape system for the Mengzhu crewed spacecraft.
That's the actual capsule that will carry astronauts to the moon, right?
Exactly. But while the capsule was being tested, the booster was essentially rehearsing for the July 10th catch.
Multitasking at its finest.
Seriously. The first stage flew back down, continuously adjusting its attitude with those grid fins, and it managed to hover a mere 5 meters above the sea surface before splashing down into the water.
And stationed right nearby, monitoring the entire descent, was the pilot vessel.
Yep. They rehearsed the entire mechanical dance. The navigation, the engine throttling, the LiDAR communication, the hovering, everything except the final physical embrace of the net.
So the July 10th flight just added the final variable of physical contact.
That's it. And it proves an entirely different path to orbital reusability. I mean, we've spent decades assuming that the limiting factor in space exploration was the rocket itself.
Right. We thought the key was making the vehicle smarter, lighter, and more complex so it could land itself perfectly on a hard surface.
But watching this 63-meter booster get swallowed by a hydraulic net in the middle of the South China Sea, it makes you realize the bottleneck is really shifting.
It's a profound inversion of aerospace philosophy, honestly.
It really is. What happens when the future of space travel relies less on the spacecraft and more on the strange, bespoke, colossal infrastructure we have to build on Earth just to catch them when they fall?
I mean, SpaceX is building massive towers with mechanical chopsticks to catch rockets on land, and now China is building 25,000-ton autonomous ships with hydraulic nets to catch them at sea.
We're moving into an era where global maritime traffic and naval logistics are going to have to account for fleets of robotic catcher ships.
Wow, yeah.
Just constantly repositioning across the oceans, waiting for spent rockets to rain down from the stars.
It completely rewrites what a spaceport looks like. Instead of a concrete pad in Florida or Hainan, the spaceport of the future might just be a shifting constellation of giant nets floating in the open ocean.
It's a wild thought.
It really is something to mull over. Keep looking up, everyone, and we will catch you on the next deep dive.